By now, I think I have repeated this point earlier also. Rotation motion in a way runs parallel to what you may call as translation motion. So whatever term we have in translation, we have corresponding term in rotation. So when we talk about, we have done for for force, the corresponding term is torque. And when we talk about momentum, this corresponding term angular momentum. And whenever angular comes here, angular basically means it gets a p multiplied by r vector. And when we say r vector, what is r vector here? R vector is with reference to certain point has to be taken as reference point. So that's why all the terms when we talk about angular motion are related to certain axis. Momentum also is not something, angular momentum depends on axis. Let's continue with that. So this is what I am today. What are we going to do here? If we look at this part, this is momentum. We are going to look at angular momentum. So basically, whenever angular momentum is present, presence of momentum only leads to angular momentum. Presence of force only leads to torque. So this is force has to be present that leads to torque. And there's something we call angular impulse. See, if there's a force here, and later on we'll come to angular impulse also, and all things are common. See, if the force acts for certain duration, becomes an impulse, and impulse leads to change in momentum. We understand that part only. See, if we understand that part, let's continue further. So force acting for certain time duration is called an impulse, and result of impulse is in form of change in momentum. So many times we find impulse in terms of change in momentum. So if this is impulse here, it has a point of action, it has a sense of direction. If we multiply by this vector here, this becomes angular impulse, and this change becomes change in angular momentum. So that is something we'll try to understand today. So every time whatever we're doing, you're multiplying with the perpendicular distance. Impulse multiplied by perpendicular distance from a particular point becomes angular impulse about that point. So every time perpendicular distance is coming into picture. So let's look at the torque. We had done torque yesterday. Torque is about a point is r cross f. So when we talk about angular momentum, I hope all of you remember, and it's easy thing to understand. There's momentum here. Linear momentum, we understand. Linear momentum is a vector quantity in the direction of motion of a particle. So similar to torque, if we create r cross p, becomes angular momentum. So we understand momentum, and so moment we write r, it is with reference to some point here, similar to this, with respect to a point. And how do you find? Rest all is very similar. The way we find direction for torque, same way to find the direction of angular momentum. You've seen yesterday I had a force vector. Now today we have momentum vector. Momentum vector also in the direction of velocity. And this is the point about which angular momentum is being calculated for a particle. Any particle, if the particle is moving in this direction, this momentum, r cross p becomes my angular momentum. And in this particular case, again, if I look at which direction, and it applies right hand, properties of cross product holds good here also. We know in case of cross product, if two vectors lie in a plane, the cross product is perpendicular to the plane. So here also, if momentum basically motion and r vector, if they are in the same plane in xy plane, cross product will be equal to either k cap or minus k cap. Clockwise is negative, anti-clockwise is positive. You can keep that also in mind. Rest all is very similar. We can similar to torque. I'll take few examples to understand that part also. Let's see here. So this is my coordinate system here, typical x and y. So if there's a particle A, which is, it has to a certain position. Where is the particle? Particle is at 0. That's the coordinate of the particle. And it's moving along y-axis. Its momentum is mv. What is this angular momentum about O? Whenever we talk about angular momentum, it is equal to this momentum multiplied by perpendicular distance. And since this is vertical here, perpendicular distance will be in the horizontal direction. So this angular momentum becomes mv into A. Angular momentum of this particle about O is mv into A. And that's what it is. And similar way, let's take other case here, and which direction this would be. So again, if we say, if this is my, if I think clockwise and anti-clockwise, if this is the arm of the clock here, and which direction it is moving, origin is taking the fixed end, tail end of the needle here, which way it is rotating anti-clockwise, this will be positive. The first one is positive. Now I come to this another particle which has momentum 2 mv. It is moving in this direction. Direction of motion is horizontal. So angular momentum multiplied by perpendicular distance from where? From about the point about which I am calculating angular momentum. So since I am calculating angular momentum from O, we will take a perpendicular distance. So we drop a perpendicular, or we understand since it is horizontal, perpendicular distance will be vertical. The distance is B. And in this particular case, it is going in a clockwise sense. So those who want to find little difficult, an R vector here. What is R vector? Position vector, tail to tail. This is position vector. So R cross momentum. R cross with this, how fingers will curl and thumb will go into the plane of paper. Third case here, there's a particle here. And this particle, the position is given, the direction is given, which direction it is tending to rotate. This also going in the clockwise direction. Distance is A, momentum multiplied by perpendicular distance from a point. So like torque also, when we talk about perpendicular distance, see it is a point here, a line. What is the line? In case of force, we take line as line of action of force. And when we take angular momentum, we take a line as line of motion. So this is line of motion, and if we translate anywhere, angular momentum does not change. And we drop a perpendicular, that's a perpendicular distance. Right, so we have done for simple cases. Let's take a random point. Suppose there's a particle M here, and it is at some coordinate AB, and it has velocity in the 2D space. We resolve velocity to two components. It has Vx and Vy. These are the velocities. What it is angular moment about origin. So in this case, angular momentum also is a vector quantity. So we can use property of vector resolution. We have broken into two components velocity. So momentum also is broken into two components. What is momentum in x direction? I mean to Vx. So when we calculate angular momentum due to this component, we ignore this part here. So what is angular momentum due to this part here? Let's look at due to x component here. Due to x component, again, it is in the horizontal direction. So we'll take the perpendicular distance from here. How do we find perpendicular distance? From O, we'll drop a perpendicular on the line of motion of the particle. When I drop a perpendicular horizontal, so the perpendicular distance will be vertical along y direction, which is nothing but B. So due to this component, angular momentum is Bx into B. And similarly, we calculate due to y coordinate. In this case here, so what will be here? Again, this case and first case, which direction? It is going in the clockwise sense. And when it was going in the clockwise sense, this will have negative part. And this going in anti-clock. Bx is going in anti-clockwise sense. Just imagine if I translate the particle, keep the particle here, give a velocity like this. How would it move with reference to this point? It will move in the anti-clockwise sense. So m into Vy, which distance now? This distance. This distance is A. So we can calculate. So Vy here, and we can calculate those things. Now coming to this is something what we have done. This we have calculated angular momentum for a particle. So we always keep in mind angular momentum. We can come across two kind of cases. Angular momentum for a particle. So what is angular momentum for a particle about origin? What you have written here? Angular momentum of a particle is equal to R, and when you take R perpendicular distance, R into mv, R is perpendicular part here. Okay, and this V also could have been written as with R omega. So angular momentum is R square omega. This is for one particle. And if there are number of particles, so if we have to number of particles are there, we take summation of all. When we take summation of all, it becomes equal to summation of mr square. What is this particle? This term is nothing but moment of inertia. So what is angular momentum of an object? We can do so when all particles have same angular velocity omega. Then object is undergoing pure rotation. In case of rotation, every single particle will have same value of omega, which can be taken as common. So angular momentum of an object which is rotating about an axis is equal to I omega, and omega is the angular velocity. I is the moment of inertia about whichever axis we are calculating angular momentum about. So two cases, one is in case of a system of particles and single particle. Now come to case, let's apply I omega case here. I omega is angular momentum of an object is undergoing rotation. Angular momentum of a rotating object, I omega, where I is the moment of inertia about axis of rotation. Let's take a simple case here. Simple case is a rod here, and it is rotating with angular velocity omega. about this mid center mass perpendicular to the axis. You can imagine this was something like a seesaw, and this is the midpoint here. And if it is set into rotation in vertical plane, what will be angular momentum here? In this case, angular momentum is a pure rotation I into omega. Which I about the axis about which is rotating. So it is rotating about midpoint. So I'll use ml square by the formula. So this is I into omega. That's the angular momentum of this rod. It is rotating about center mass. If axis of rotation is shifted, of course, what will happen, even if omega is same, if axis is shifted, I will change. And I will change, angular momentum also will change. So we understand angular momentum depends on axis of rotation. So suppose axis is not here, it is rotating same angular velocity, same rod, mass is same, length is same, only thing axis of rotation has shifted. And we understand what will happen here. See, in this case, you notice when we rotate, the different particles we rotate with velocity, something like this. Velocity will keep increasing. Maximum velocity will be equal to L by 2 omega here. When we shift this axis here, this particle have acquired higher linear momentum. And angular momentum also will increase here. What is the angular momentum of this axis here? We have to find moment of inertia also about this axis. How do we find moment of inertia? Using parallel axis theorem. So in this case, angular momentum will shift if this direction L be through. We have seen this angular moment, we have done moment of inertia yesterday also, something similar. So this moment of inertia comes equal to ml square by 9 and into omega, that's angular momentum. So two things, angular momentum for a particle, angular momentum for an object which is rotating about fixed axis. And we should know how to calculate both. And they're simple enough. Let's take a particle is moving in a circular path of radius a. So this is the center, radius is a, and this is the path it is moving. This is a particle p which is undergoing circular motion with a constant velocity of magnitude v. So basically, constant velocity may not be the right term, but whenever we use velocity term in this course, it implies we are talking about a magnitude of velocity. So magnitude of velocity is v. Center of circle is marked as c. What is the angular momentum? About this point origin. Angular momentum, we can calculate angular momentum about C also. We can calculate angular momentum about O also. So let's say this particular instance of time, center is not the origin now. Center is somewhere here. The coordinate of the center will be equal to A naught here, A0 here. What is the angular momentum when particle is at this particular position? So angular position of the particle is theta. What is it angular momentum? And we know at this particular instance, how is it moving? It is moving in a circular path. Velocity v will be perpendicular to CP line. So where depends, so angle theta. So what we know here, if this angle is theta, this angle will be equal to 2 theta. Okay. So we can, one way of solving what we can do here, we can, when we know this velocity, we know its direction with x-axis, we can take two components. We can take its x component, we can take its y component, and we can find angular momentum about O. Because to find angular momentum, we need components of velocity and its coordinate. We can find coordinate also, and we can find components also. So that's one way you can find using component of velocity and p, we can find angular momentum. And we have given a simple example. And the second thing, can we also use I omega here? So we have also said you can use I omega. Even a single particle also have moment of inertia. And what is omega here? Can we do that as well? Yes, even that also is possible. How do you do that? Even a single particle also. What will be its moment of inertia? So it's moment of inertia of single particle about O. So I have to find angular momentum about O. This moment of inertia of this particle also find about O. So moment of inertia will be mass into square of distance from axis OP square. And how much is OP here? And this side is A. So what do you do here? If you drop a perpendicular, this angle is theta. Half of this length becomes equal to A cos theta. So A cos theta is the distance. So this is the moment of inertia. But what is angular momentum as seen from O? As soon as from O, angular momentum about O is equal to d theta by dt. That's angular velocity about O is equal to d theta by dt. But what is angular velocity about C? Angular velocity C here, if this angle is theta, always if relationship in this will be twice of this. That will be equal to d into 2 d theta by dt. That will be equal to 2 d theta by dt. We know d theta by dt. Angular velocity about point C is known. What is angular velocity about point C? Angular velocity of point C is equal to 2 into v by a. That's angular velocity and d theta by dt. So we know, sorry, what I'm saying now. What is d theta by dt? D2 theta by dt. This angular velocity we know. What is this angular velocity about point C? Angular velocity point C is v by a. So we know this value. What will d theta by dt? Angular velocity about point O will be equal to v by 2a. Because here the angle is half and the rate of change of angle also will become half. Very easily you can arrive at. So this value is theta. So basically this implies d theta by dt is omega v by 2a. So angular velocity about O is equal to v by 2a. So can you find omega is omega c v by 2a, omega c by 2. And so what is angular momentum about O? I into omega. I multiplied these two. So I can find in this fashion also I omega. We could have also found out using velocity and its components. Because our angles are known, all in terms of theta, we can write those components and find the number. Okay, and this case, let's say a particle is moving along the sides of a square. So this is a square here, and A, B, C, D. Each side of the square is given a side is A. And what else is given? It is an XY plane. Coordinates of point A is given. This point is coordinate is RR. Okay. So this is what is given. Find angular momentum L about origin, different parts of motion. When it's moving from A to B, as it moves from A to B, between A and B, velocity is constant. If velocity is constant, it is having, whenever velocity is constant, it is having linear motion, constant velocity. Angular momentum remains constant. Reason is very simple. When velocity is constant, no force is acting. If no force is acting, momentum is not changing, angular momentum also is not changing. If no force is acting, torque also is zero. So angular momentum between A and B will not change. Anywhere will have same angular momentum. So let's see how do we calculate angular momentum when it moves between A and B. At every point, its angular momentum is constant. About O. Okay. So in this case, so again, what we need here, we know momentum mv. We only need perpendicular distance here. So every time, see, all cases, the momentum is mv in the direction of arrow. To find angular momentum about O, we need to find perpendicular distance. So when it is moving along AB, this is the line of motion. And if this is the line of motion, what is the perpendicular distance of the line from the point O about which angular momentum has to be calculated? The perpendicular distance is R here. And which sense it is moving? It is moving in a clockwise and perpendicular distance is R. So every part, these are done for AB. We can repeat the same for all four parts. What are two things important? We need to find clockwise or anti-clockwise. If it is clockwise, sign is negative, minus k cap. If it is anti-clockwise, it's plus k cap. We need to find the direction. And since magnitude of momentum is same, we just need to find the perpendicular distance. So these are the only two things we need to find for AB. Let's do for BC also. BC, what is the motion? This is the direction of motion. So again, this is the line of motion. We drop a perpendicular from O. If I drop a perpendicular from O, this would be the perpendicular distance. How much will perpendicular distance? This distance is R plus A. Perpendicular distance will be R plus A. In which sense it is moving? It is moving in this sense. What is this sense? Anti-clockwise. So between B to C, it is anti-clockwise. Perpendicular distance is R plus A. Similarly, I come from C to D motion. C to D motion, this is the line of motion. So see, every time for finding angular momentum for a particle, it's a very simple thing. Just it is finding distance of a line from a point. That's what angular momentum of a particle is, if figure is given. Either we have to use a cross product or we have to use what you may call as a figure with perpendicular distance. So when we talk about angular momentum, what should come to your mind? Angular momentum is momentum multiplied by perpendicular distance. Perpendicular distance of a line from a point. Line is line of motion. Point is point on the axis about which angular momentum has to be calculated here. So in this case, which direction it is moving? If I translate it is moving like this. Which direction with respect to anti-clockwise? Perpendicular distance R plus A. And finally, when it's moving from D to A, this is the line of motion. Perpendicular distances, it is moving in the clockwise sense. This is the direction of motion. If it continues moving here, when it comes here, which direction it is going? It is going in the clockwise sense. So clockwise negative, perpendicular distance is R. Okay, so finding angular momentum of a particle should be a cakewalk. Okay, and if I ask one more thing here, what is happening? Between A and B, angular momentum is constant. But as suddenly it moves from AB to part BC, angular momentum must be changing, and momentum is changing definitely. If momentum is changing means at point B impulse is active, point C also impulse is active, and if impulse is active, it will be angular impulse also. So what is the impulse which have acted on the particle at B? Impulse which have acted on the particle, this velocity which was having, it had momentum in x direction which has become zero. Why it has become zero? Uh, Impulse which have acted in this direction. And it has acquired momentum in this direction. This is the type of impulse which have acted at point B and B. So if you have to calculate what is the angular impulse is equal to impulse multiplied by perpendicular distance. So I can calculate angular impulse also. We'll come to some cases later. So angular impulse also, to B point some angular impulse have acted. C point also impulse have acted, hence angular impulse also acted. And what will be the angular impulse here? Angular impulse, I know what is the angular impulse at B. Angular impulse at B will be change in angular momentum. I have angular momentum from BC part. From this angular momentum, if I subtract this angular momentum, that will give you change in angular momentum. And change in angular momentum has to be equal to angular impulse which have acted at B. Okay, so change in angular momentum. So we can, once we write all this term, we can easily get that also. All cases, when we talk about angular particle, when we talk about angular, every time the equivalent linear quantity, we are multiplying by, in terms of magnitude, r perpendicular. What is r perpendicular? Line and a point. So line is what? In case of torque, line of action of force. In case of whenever momentum quantities are there, line is line of motion. Which is the point? Point is about which angular quantity has to be calculated. Angular momentum, angular impulse, nothing but finding perpendicular distance, clockwise, anti-clockwise. Only two things we need to figure out for all such motion which is taking place in a plane. Now, this is something that so far what we have done, it was in a plane. Now we can have some cases where it is in 3 dimensions. So let's try and understand this is a conical pendulum. So I hope all of you understand this is a point of suspension O, and this is x-axis, y-axis, z-axis, and it follows right-hand thumb rule. So if we fold my finger from x to y, thumb will be along upward direction. So it is a typical conical pendulum. O is the point of suspension. What else is given? Mass is m here, and strong is a sling of length L. So length of the string here is L, and it executes a circle of radius R. So this radius of circular motion in horizontal plane, of course, this particle is undergoing motion, moving in horizontal plane, and radius of circular motion from this point O dash, which is central circle, is R. And what we need to do here, it has speed v. Of course, circular motion basically it is having uniform circular motion in horizontal plane. Hence, speed will be constant, which is v. At time t, mass is where. So at time t, that's what we. This question related to this particular instance of motion. At this particular instance, it is just crossing. Which axis it is crossing? It is just crossing x-axis. So what is its position? Mass is a positive ri. This point is at ri cap, having velocity v j cap. Of course, velocity will be perpendicular. This is velocity is along j cap. Position is ri cap. That's what is given. At this particular instance, what is the angular momentum vector of mass m about O, point of suspension? So I have to find L about which point? About O point. Okay. How do you find angular momentum? This is involves 3 dimension. So we will not do in terms of momentum into perpendicular distance, because we may need answer in terms of ij cap. So when we calculate this quantity, immediately what should come to mind? Any angular quantity, r vector first multiplied by momentum vector. What is r vector? R vector is position vector of the particle, taking which point as origin, point about which angular momentum has to be calculated. So R is nothing but which vector? R is OM vector. Position vector of the point with O point as a reference point. This is my R vector. So all I need to do, I need to write velocity, a momentum in vector form, and OM vector. I take the cross product. I'll get this vector. So what is position vector of M taking O as origin? See, if O was not an origin, OM vector would have been what? I could have, this is something I could have taken this vector also, I think. So what is R vector here? This vector I can write as OO dash vector plus O dash M vector. What is OO dash vector? It is downwards minus K cap direction. And how much this length will be equal to O dash minus K cap plus Ri. And what is OO dash? OO dash is nothing but this inclined length is R, L, this is R. So this particular vertical side will be equal to root of L square minus R square. This one is very simple. So this question was only, trick was writing this position vector, understanding which position vector has to be taken and writing this position vector in vector form. So I have written this OM vector as O dash vector plus O dash M vector. And once we write this vector, angular momentum is equal to R vector, this vector here, cross multiplied with momentum vector, MV J cap, the same direction, velocity, and rest all is finding simple cross product. And okay, so in this case, yes, of course, we get the angular momentum, and angular momentum is changing. What is the torque about O dash? So in this case, this angular momentum and angular momentum will keep changing here. Why is angular momentum what changing? Because the torque about O is not equal to 0, hence angular momentum is changing. Magnitude is same, the direction is changing. So angular momentum is changing. And in this case, if I have to calculate torque about O, it's very easy to calculate torque about O. Why it is easy to talk about O? What is the torque about O on the particle? On the particle M, forces are acting, mg is acting minus k cap direction, and tension force is acting, and tension force direction is passing through O. So tension is not creating any torque here. Torque is created only by mg vector, and its perpendicular distance is r. We could have easily calculated torque also. In this case, it's a little bit of 3 dimension. So torque also we could calculate here. Torque would be, yes, we can write position vector into force here. What is the force here in this case? Force will be equal to minus mg. We can calculate torque. And since the torque is acting, torque is non-zero, and this also will remain, angular momentum will keep changing. But if I take what is the torque on point M, about point O dash, if I talk about O, how did I calculate here? Two forces, T force and mg force. If I have to calculate torque about O dash, what is the torque about O dash? I'll give an answer. Torque about O dash is 0. Why is the torque about O dash is 0? Since it is going circular motion in horizontal plane, forces are acting. Now I'll directly take the resultant. I know what the resultant is. The resultant of these two forces is equal to what? It is having circular motion, this particle. So net force is always acting towards center. Resultant of T and mg. Since it is acting towards center, it will pass through O dash. So torque of net force about O dash will always be 0. Hence, angular momentum about O dash will remain constant, which can easily be calculated. If I have to calculate what is angular momentum about O dash, how would I calculate? I will have to write R vector into momentum vector. Momentum vector will not change, R into P vector. But what would be the position vector of this particle with reference to O dash? O dash, this is a position vector. What is position vector? Ri cap. That's a position vector. In this case, if I have to write I here, I would written R vector is equal to R I cap at this particular instance. And what is the momentum vector? Into the same thing, MV J cap. And this will remain constant. Which direction it is pointing? It is pointing towards J cap, and this any point it will remain constant. It doesn't depend on angular position. Angular momentum at O dash will remain constant because torque about O dash is 0. I think only thing you understand why is the torque 0, because this question also is coming J advanced ones, torque about O and torque about O dash. You understand why, how we calculated torque and how it can see calculation of torque is again identify the forces and either write in vector form or take the perpendicular distance. So previous case I have taken split into two forces because that was easier. When you calculate what O dash, I have taken the resultant force, and because it becomes 0 in that case. Now coming to angular momentum, we had done angular momentum due to of a particle due to translation. We had done angular momentum due to rotation. What happens when angular momentum object has translation as well as rotation? So far what we have done, if I have a disk, I rotate the disk about some point rotation, or I translate the disk. What happens is like a car tire. Car tire has a rotation omega also, and its center of mass also is moving. So it is having rotation motion about an axis which itself is under motion. If I represent such kind of motion, combination of translation rotation, you have V term also and omega term also. How do we calculate angular momentum where translation and rotation both are involved? So I'll keep this one, just pay that attention. This point also, this is the most important point related to combination of translation rotation. See, how do we deal with 2D motion? 2D motion we deal with as 1D motion. So it becomes 1D motion in one X direction, 1D motion in Y direction. We split into two parts. So even all 2D questions can be treated, or they can be dealt with or analyzed by considering motion independently. Something similar we do in case of rolling. What we do, we take a motion of center mass. We don't look at the rest of the object. We just look at how center mass moving. And center mass is a particle, it will always have a kind of translation motion. A point itself cannot have rotation, it has always translation. So we look at translation of center mass, and then we, a second part. So here we split into XY component. In this case, we split into translation of center mass and rotation about center mass. These are the two parts we split into. So when we calculate into angular momentum due to translation and rotation, we calculate angular momentum of motion of center mass. So when I'm calculating motion of center mass, I'm not looking at, I'm just looking at this point, center mass. So this is like when I'm calculating this mass m is moving at this velocity v. And then I calculate, okay, this becomes line of motion. About whichever point I have to calculate its angular momentum of the particle, it's just the perpendicular distance. And when I come to rotation, it's just I omega. And I add it up with sine. So both are vector quantity. So what is resultant quantity? We add up with sine. So that is the most important property we need to keep in mind while dealing with combination of translation and rotation. Translation of center mass, basically we can also call it what is the motion of center mass and motion about center mass. Motion of center mass is translation, motion about center mass is rotation. Two parts, and then we add it. Okay, let's take it. This is uniform disk. MR is undergoing translation. Yes, so what is the doubt?
So, but every point which is on the sphere, like apart from the center of mass, won't it have like an angular momentum about the origin?
Yes, basically, but when we see, it will have two motion. So different parts will have different velocities. They will have different angular momentum. But if we calculate, I think we are not going to the proof, but when we calculate angular momentum of different particles on an object, it is not only circular motion, it could be any odd shape. Any odd shape, there are two things here when we talk about rolling or combination of translation rotation. And if we suppose we take a kind of any odd shaped object, you have cricket bat. You throw the cricket bat in air. And when you throw cricket ball, it will have very odd kind of shape. But in any instance, different particles will have different velocity. But if I just look at its center of mass, at an instance, center of mass will have particular direction of velocity. And if I know motion of one more particle, I can find its angular velocity with reference to center mass. So if I find velocity of center mass, and if I find angular velocity of any one particle, all angular particles will have same angular velocity, which you can very easily prove. If you're interested, it takes less than 2-3 minutes, you can prove that one. So once we have velocity and once we have angular velocity, when we check every single point, if I calculate what is velocity of this point, it will be equal to v vector plus r omega vector. That will be the exact velocity of every single particle. And this is something, this can easily be proven. So we use, that's why since the result comes something like this, we use that result here in analysis of motion. Any complex motion, any rigid body is velocity, if we know omega and v, every particle, what instantaneous velocity will be vector sum of the two. So that's something proof we are not going now, but this is what the result is. And it holds true, and the simple reason also why it holds true. It will hold true only when the object is rigid. Okay, so this motion, so if we have omega and L, so let's see what is the angular momentum. There's a disk here. It is having, so when I look at the center, I look at two things here. So how do you look at what does omega mean? Okay, at this particular point, if I'm looking at only at the center mass, I see it having some path. And instantaneously, whatever path you have, any instance, it will have a linear motion only. Instantaneous velocity, it will have this velocity, instantaneous velocity of the center mass. Any particle will always have, even if curved path also we had dealt with earlier, if you take a small instance of time, any curved path also is a linear motion. So it has velocity omega, and all particles are having angular velocity omega which refers to O. And which is pretty simple. See, if I take any three particles, if I take particle A and particle B and the center mass, okay. So if I connect these 3 points here, it will form a triangle kind of thing. So if a line OA is rotating with angular velocity omega, AB also has to rotate and OB also has to rotate with omega. Basically, if this also rotates with omega, angular velocity of B with reference to also is omega. All particles will have same angular velocity. Very easy to prove, it is a rigid body. Okay, so coming back to this one, so if this is momentum, how do we calculate angular momentum? I'll calculate angular momentum of the particle which is central mass. What is angular momentum about O? This is mv into perpendicular distance. What is perpendicular distance from where? Perpendicular distance about point from which I have to calculate. First, what is angular momentum about origin? If I have to calculate angular momentum of origin, I'll take the perpendicular distance from origin. And since it is moving along the line y is equal to r, perpendicular distance is r, and it is moving in the clockwise sense. First one, motion of center mass of the particle, translation motion, minus mvr k cap. Okay, so that's the direction. Velocity is along I cap direction, and we can find easily sign motion is an xy plane. That's why it is coming as k cap. Negative sign because it is clockwise. Okay, and this is due to translation. How about due to rotation? It is having angular velocity omega. And about which point? When we take rotation, it's always about center mass. What is this image? If it is an angular velocity omega, I will take about center mass because I have to calculate rotational angular momentum about center mass. So moment of inertia about center mass perpendicular to plane, mr square by 2 omega k cap. So this is sum of these two becomes the combined angular momentum. Let's take part B. What is the angular momentum not at this origin? If I take angular momentum of some other point B, which is 0 r0. If I take this point, what will happen? The perpendicular distance of line of motion becomes 0. This point lies on the line of motion. This term will become 0. Angular momentum due to rotation will not depend on choice of this point here. This term will remain same. This term will, because perpendicular distance is varying depending on choice here, this term will keep on changing here, here, and here. Other term will remain constant. So in second case, angular momentum due to rotation about center mass remains unaffected by the change of reference point. So the translation becomes 0. It is if it is about this point. If I continue part C, what is part C? Part C is what is angular momentum about point which is 0 to r0. So if this is the point here, this is the line of motion. With respect to this point, how is it moving now? See, with respect to this point, it was moving in the clockwise sense. With reference to this point, it was moving in the linear direction. It has no rotational time. From this point, how is this point moving? If this point moves further, the r vector is rotating in the anti-clockwise sense. This motion is more like, or if I translate here, this motion, if I say this line of motion, and how is it moving with reference to this point here? Anti-clockwise sense, perpendicular distance is r. So third case, this motion mvr, it becomes plus minus mvr k cap. Second case it becomes 0. Third case it becomes mvr k cap. So translation moment of angular momentum depends on choice of origin. Rotational angular momentum, since it's rotating about center mass, it doesn't matter what the axis is. So we are calculating angular momentum due to rotation about center mass. It doesn't depend on all three cases, that remains same. So if we understand this part, this is the most important point to understand about angular momentum of an object which is having rotation as well as translation. We'll split into two parts. At a time, you look at So this figure, if you show wish, we can also draw something like this. In case of translation, how could I have redrawn this figure? Either I redraw the figure or this what I keep in mind. In case of translation, it's a point which is moving with velocity mv, along which line y is equal to r. So this what? So, this part when I'm calculating due to translation, I can convert into problem of calculation of angular momentum of a single particle. Single particle momentum multiplied by perpendicular distance. That's all. Okay. Now, when you have angular momentum, similar to linear momentum, when is linear momentum constant? Linear momentum, we write something like this. When is the linear momentum x component constant? This is constant when summation x component of forces is equal to 0. So this is equivalent of this if we write here. This linear momentum remains constant when component of force in that direction is 0. Similar, if you write conservation of angular momentum of a system about an axis, because here every time axis is important, it will remain constant when in place of force, when torque about that axis due to external forces is 0. So they have different waves. So it is related to particular axis. Angular momentum about an axis. Angular momentum also with reference to the axis, and torque due to external forces about that axis. If torque due to external forces about that particular axis is 0, angular momentum about that axis also will be 0. But if there's no external force acting, then there's no torque. Angular momentum is constant about any axis. Let's take some simple example of this conservation of angular momentum. And this is something you can easily visualize if you have a rod here, rod into set into rotation. And we have done something similar if we have two beads and rod has mass is 12L, 12M is the mass, L is the length here, it is set into rotation in horizontal plane, angular velocity omega. And if we have two beads near the center, as we set into rotation, if we give them small velocity, this is because of centrifugal force, or this will slowly keep moving out. And what will happen as they keep moving out, because both masses are same, both will at a particular instance, they will have equal distance. And what we need to find here, so initially this was angular velocity omega, and find the final angular velocity, not angular momentum. We can angular momentum will remain same. Angular momentum, sorry, I'll change this one. What is the final angular velocity when rings reach the end of the rod? So how would figure look like when this is the initial state? When initially this is where the rings are, and angular velocity is omega. Now what we need to find here, when the rings have reached almost the end, angular velocity will not remain same. It will become omega dash. But let's see what has happened in between. In between, when it is rotating, what are the forces which are acting here? Forces acting are basically gravity is acting in the downward direction. Reaction is acting in the upward direction. As it moves, also the gravity will act here and gravity will act here. And both cases, torque created by gravity will be 0 about center, and the reaction also will create 0 torque. So as it moves, the internal forces, contact force acting between the ring and the rod, and those are internal forces. I will not consider those internal forces. Torque due to external forces about any axis is 0. Angular momentum remains constant for ring and a rod as a system. If I take ring as a rod as a system, angular momentum is constant. So let's write what is the constant ring and rod as a system. What is initial angular momentum? Initially, when it's set into rotation, this is example of pure rotation. So angular momentum will be equal to I into omega. Since system consists of rod and the ring, moment of inertia also will take of rod as well as of ring into omega. So when the ring is, see in this case also radius of ring is not given, size is not given. So we'll assume the radius is too small. We'll consider only as a particle here. So initially, two rings are very close to the axis of rotation. The distance from axis is 0. So moment of inertia of two rings is 0. Moment of inertia of rod is ml square by 12. We'll take ml square of what? M into L square by 12. So it becomes ml square omega. That's the initial angular momentum. When rings have reached a end here, what has changed now? Omega dash has changed. The reason omega dash changed, because mass is farther away from axis of rotation. As mass becomes farther away, moment of inertia increases. In this case, moment of inertia of the rod remains same, but this ring here, this mass is at a distance of L by 2. So its moment of inertia become m into L by 2 square. The other one also m into L by 2 square. So total moment of inertia into m into L by 2 whole square. This is the new moment of inertia. And so we equate the angular momentum, initial moment of inertia into omega, final moment of inertia into omega dash. We can find out what is the final angular velocity. And that's a typical example of conservation of angular momentum. So whenever I changes, correspondingly omega also has to change. Next question is,
So if we had a mass like m and 2m on either side, we can't use this conservation of angular momentum.
Still angular momentum will remain conserved here also, even there also. Why it will
That's
remain
because the
conserved?
normal force will.
Yeah, this forces will act and cancel it out because those cannot act in that direction.
Okay.
Okay, those are little complex. I'm not touching on that, but yes, even then also it cancels out. Because of the hinge arrangement. Okay. Like the door. Let's come to this question. If linear motion, we are at the topic of conservation of angular momentum. So let's say what happens in case of collision. We are taking case of oblique collision. Ball comes and strikes the surface and bounces back. So we have known in case of linear motion why the momentum has undergone a change. The surface is smooth. Force has acted for certain duration. So I can understand the force, or if I take force into duration together, impulse have acted in normal direction. That's why there's change in momentum. But whenever this impulse, depending on choice of axis, there's an angular impulse also. And whenever there's a momentum, there's an angular momentum also. So whenever momentum exists, depending on choice of axis, angular momentum also exists. And whenever there's impulse, there's an angular impulse also. Only thing what we need to do, what is the angular momentum? Perpendicular distance. Momentum into perpendicular distance. Impulse is there. Impulse into perpendicular distance becomes angular impulse. Every time you multiply the perpendicular distance, and the distance will depend on which axis do I choose here. Ball moving the construct, it is something bounces off here. So in this case, about which point can I conserve angular momentum of the ball? Okay, which point I can conserve angular momentum? So let's see here. So if I take if angular momentum will remain constant, two ways I can think of. Angular momentum will remain constant. Two ways I can think of. What are two ways I can think of? Similar to linear momentum. When does linear momentum changes? When force acts. See, we take linear momentum equal, what we say, F is equal to what? F we write equal to dp by dt. So when there's no force, momentum will not change. And other way write is F dt. When there's no impulse, the linear momentum does not change. Similar way we can take here also. When would L remain constant? Either I can say when there's no torque, it will not change. Or I can say when there's no angular impulse. Both are similar here. So now look at which axis will the angular momentum remain constant. It will remain constant about an axis about which torque is 0. So if this is the direction in which force is acting, if I take any point on the line of action of force, the torque about, so if I take the torque of this force, normal reaction about B is 0. So torque about B 0, this angular momentum about B will remain constant. But when I take about A, torque of normal reaction about A is not 0. A is not on the line of action of the force. So it will have a perpendicular distance and it will have a torque. And when the torque is existing, it will change. So which axis, if I take three axes about A, B, and C, which axis will the angular momentum of the ball during collision or after collision remains conserved? It is about B only. Okay. Let's come to some more question. Let's see. This is also very common kind of question. Let's understand here. Rigid spherical body spinning around an axis. And this very common example of spinning we take, we are seeing those kind of dancers also, ballet dancer. They stretch out their hand and they start rotating. And then what they do, they pull hands together and they become like a vertical rod kind of thing. And when they stretch out their arm, moment of inertia is high. When they bring their arms close to the body and become like vertical, I becomes less. When they're rotating with initial omega naught, these two product of these two is constant. So when they bring their arms close to the body, another I becomes less and omega increases. This also is example of a rotating ballet dancer. It's conservation of angular momentum. Several things we can think of. So let's take a rigid spherical body spinning about an axis without any external force. And spinning due to change in temperature, its volume increases by 3%. So temperature increases, thermal expansion will take place. And as the volume increases, naturally what will happen? The linear dimension also will undergo change. So if volume increases by 3%, if you recall, what is volume? Volume is, okay, the sphere volume is 4 by 3 pi r cube. So there's a 3% change in volume. There has to be 1% change in radius also. What is the percentage change in angular speed? First thing, how do I solve this question? Since no external torque is acting, this question about conservation of angular momentum. So angular momentum remains constant, and if angular momentum remains constant, means I1 omega 1 has to be equal to I2 omega 2. That's the question. That's how we need to solve it. And why would omega change? Omega will change because I is changing. And why is I changing? Because linear dimensions are changing. So let's try to understand what will the change in I. So this relationship I is like this. What is delta by I for small changes? Mass is not changing into delta by R. And change in linear dimension is 1/3 of change in volumetric dimension. This equation I could have written as delta V by V is equal to 3 delta R by R. So delta by I is equal to, this is what delta by 2 into delta by R. Delta by R can be written as 1 by 3 delta V by V. So volume changes by 3% is because radius has changed by 1%. Radius has increased by 1%. Now we can simple term, we can substitute here. This is based on delta I plus delta omega by omega is equal to 0. Angular momentum is constant. So we just substitute this term here. We find what is the percentage change in omega. Very easy to find. That will be 2%. And if I has increased, it will decrease by 2%. What are other examples of conservation of angular momentum? This is also a common example. And suppose a vertical rod, and it's this kind of devices are there, and you can also set up as a device like this. To a smooth vertical rod, I can run through two discs, and disc one, first one I1, it is set into rotation with angular velocity omega 1. Other one is I2, angular velocity omega 2. They're independently rotating. What happens if we bring them in contact with each other? We just push it down so that they come in touch. As soon as they come in touch because of friction, what happens? The one which is having higher angular velocity will tend to slow down. One with a lower angular velocity will speed up, and until this will continue until slipping is there. Moment slipping is not there, it will come to both will start rotating the same angular velocity. So in this case, what is happening? Different point when the force act, we have done a similar mop kind of question. So due to friction, torque will act, and whatever torque acts on one direction or one, other one will act in the opposite direction. Or if we take two of them together as a system, torque is due to internal forces. No external torque will act. So together as a system, angular momentum is conserved. So how would I write this equation? If both omega are in the same direction, I would write angular momentum, initial angular momentum, I would have written something like this. Initial momentum is I1 omega 1 plus k cap only, because this is rotating in that sense. And this is also I2 omega 2 k cap. And when they come to when they start rotating, after some time, what is the common angular velocity will they rotate with? When they start rotating the common angular velocity, okay, so I can take, it will be equal to I1 into omega naught plus I2 into omega naught, whole thing around k cap. I can find what is the common angular velocity. After they require, they start the slipping stops. Similar, this one case when both are rotating in the same sense. What happens if this is rotating in this sense, other one is rotating in the other sense? So if we look at direction of angular momentum of this is plus k cap, and direction of this angular momentum is minus k cap. When I write is initial angular momentum, I will write is equal to I1 omega 1 k cap minus I2 omega 2 k cap. that will be equal to final angular momentum. And if their initial angular momentums are equal and opposite, what will happen when we bring them into contact? Both will come to a stop. And this is something, this is also case of angular momentum. This is one same axis, but sometimes you may also think of, if one of you has set a disk in rotation like this, other person also set a rotation like this. What happens? You bring these two disks in contact with each other. When you bring in this contact, what will happen? If the contact point velocities are not equal, friction will start acting. But in this case, angular momentum is not conserved, because when they come in contact here also, what will happen? You have to apply some force here. Then only this two, there is basically axis will remain vertical, and here external torque will act. Only thing what happens, if in this case, if I look from the top, I didn't draw that figure. If I look from the top, it's something like this. You think of it. What is happening here? If two disks are there, and I'm rotated one in this direction, and this is angular velocity omega, and if I rotated it some other one with angular velocity omega. Let's see, this radius is r1, and this radius is say 2r. What happens when we bring them in contact? Which side the friction will act? This is the point of contact. So friction will act depending on what is the at point of contact, what are the velocities these two have. This velocity is r omega, and this velocity is 4 omega. What happens? This one is moving faster. The friction force will, how would the friction force act on two of them? Friction force on the right one will act in this direction, and the left one will act in this direction. So faster velocity slow down, slow velocity speed up. So at any instance, friction force will then, so this friction force acting. So what we understand, if I take the left disk, basically force is same, but torque acting on the left disk will be equal to F into R1. Torque acting on this two. Force is equal and opposite, but torques are not equal and opposite. Torques are not equal and opposite. So torque will depend on the distance also. So this one you can calculate after some time. This is a different kind of question. Here also we can, if the radiuses are equal, if radiuses were equal, torques also would have been equal and opposite. If torques were equal and opposite, okay, then we can calculate what how if torques are equal and opposite, and if the friction force is known, we can calculate what will the angular velocity of this one after time t, and what will the angular velocity of this after time t. Torque is known. Once torque is known, we can find out angular acceleration. And angular acceleration known, we can find out angular velocity as a function of time. So this question is different from other two questions. This question, angular momentum is not necessarily conserved. Okay, some more questions were there on conservation of angular momentum. Okay, well, a very quick look at this here. Angular momentum, see, you can imagine this is a disk which can freely rotate about vertical axis. Just imagine this is like a turntable. You are standing on the turntable is at rest. So your person is standing here. What happens if you start walking on the turntable? You start walking on the, and you are walking along the perimeter so that your motion also is circular. When the turntable, if it is free to rotate, will it stay at rest? No. When you are walking, what is happening? Your feet is applying a force on the disc in the direction, and disc applying a force on the other direction. So there's a force acting at the point of contact, and the force acting are equal and opposite. And this is the force are acting at the same point. If I calculate torque about the center, due to force on the man and force on the disc, both torques will be equal and opposite. But if I take man and the disc as a system, no external torque is acting. So that's what will happen if man start walking on the disc. So a circular platform is mounted on a vertical frictionless axle. Radius and moment of inertia is given. If this man start walking with velocity of 1 meter per second, what is the angular velocity of the platform? This platform also will start rotating with angular velocity omega. So in this case, if I take man and platform together as a system, the angular momentum, since the external torque is zero, angular momentum also remain conserved. How would I calculate angular momentum of the man? Angular momentum of the man I'll calculate as a particle. Man is moving with velocity v, if mass is m. What is angular momentum? Angular momentum of the man is equal to mv into perpendicular distance r. So angular momentum of the man, moment of inertia of the man, I can angular momentum of the man. If I write, either I can do R into mv. And what will the angular momentum of the disk here, or platform here? It will be equal to I omega. And these two have to be equal and opposite. By equating these two, I can find out what is the angular velocity of the disk. Okay, and even man also, I can treat as a man also like a rotation motion. How do I treat man as a rotation motion? And man's angular momentum also I can write as I omega. What I should I take? Man also like a particle. Man also is mass of the man into r square. That's the angular, this is the moment of inertia of the man. I could write in this fashion also. I can treat as a particle also. Both ways you get the same answer. So moment of inertia of the man is this. Angular velocity of man is so much. And similarly, we can find out angular velocity of the platform. Okay, and the second part here. Okay, I think we are almost out of time. So I'll stop here. I think there are a couple of things more I wanted to do, but not be able to finish in this session.